Okay, so I'm André Silva, a final year PhD student in Portugal, in Instituto de Astrofísica e Ciências do Espaço. And today I'll be talking a little bit about our new model, which is a fully Bayesian radial velocity extraction model, present some of its first. Yeah.
I'm working on it right now for you. No? There we go. Can you
Okay, so let's start. Not from the beginning, I said my name, so everything should be fine. So as I was saying, oh, it's not showing on Zoom now. No, it's okay?
Is it okay?
Yeah, I think so. So for the third time, so I'm going to talk about our first steps towards a fully Bayesian radial velocity model that we are now starting to implement and showcase some of its preliminary results on simulated data. So I think most of you know what radial velocities are. So most of you know what radial velocities are, but just as a quick refresher on template matching. So the main idea behind template matching is that we try to align a very high signal to noise stellar template with the individual observations that we have of a given star. Typically, this is done in an order by order basis, providing us independent measurements of the radial velocity value, which will then be combined through, for example, a weighted mean to get the final radial velocity value. This is typically used and it often works better than the CCF, mainly for the M-type stars, but it does have a few flaws. The first one is that we are assuming that the stellar spectra is constant through time. Our stellar model is invariant in time, and we know that is not true. On top of that, it is not always clear on the best way to propagate uncertainties in our model from the raw stellar spectra towards the final radial velocity estimate. In order to mitigate this last point, we have somewhat recently developed SPART, a semi-Bayesian template matching algorithm, which at its core assumes that the difference between this stellar template and any given observation is a single radial velocity shift that is independently of wavelength. Again, this is in line with what we know about planetary companions. We wouldn't expect a planet to have a different radial velocity impact at different wavelengths. And so this should be more close to reality than having independent radial velocity shifts. Obviously, we still have the impact of stellar activity, but we'll assume it will be averaged out in this model. In the paper, we showcase the results on an espresso dataset of about 30 different targets, ranging from M to Gs. And similar to what we usually expect for template matching, we found a very big improvement for the M-type stars with an improving precision of about, a decrease in radial velocity scatter of about 10% compared to the CCF, and the gain in radial velocity precision of about 2 times, which was a very impressive result. For the K-type stars, we also find some slight improvements of about 5% in radial velocity scatter, and we gain a few centimeters per second in radial velocity precision in median across this data set. More recently, EPRV was also featured in the detection of Proxima D, the candidate planet with a 5-day period. We managed to find this around 40 centimeters per second signal in Proxima system using Espresso data. In order to rule out the non-Keplerian nature of this signal, we could also divide the stellar spectra into 3 different wavelength bins, and we applied the full Gaussian process model that Frey et al. Used for the detection of Proxima D to each one of the intervals, and in all of them we are able to retrieve this 40 centimeters per second signal, which does show that it shouldn't be a product of stellar activity. Even though EPRV has been working very good, it still has a few core assumptions that limits its applicability. In the first place, we are still keeping this assumption of a time invariant stellar template. And on top of that, we are not truly working within a Bayesian framework. We are sharing data between the model, the stellar template, and the data with which the model will be compared to the different observations. However, and as in most cases, the stellar template has a much larger signal to noise than any given observation. We tend to ignore this problem because the information of a single observation will be drawn out in the middle of it. However, it is not the most optimal choice, and so ideally we would move towards a fully Bayesian model. And for that effect, we could draft a sort of a wish list of features that we would like to have. The first one, and the most obvious one, is to model the stellar spectra under a probabilistic framework to avoid this dependency of the model and the observations. One option to do that is using Gaussian processes to model the stellar spectra. And in fact, this idea is not new. We could find it in Rajpal et al. And Czekal et al. In 2017. In our model, we will take the same methodology as Czekal, and the main idea behind this is that we have multiple observations of the same star. And so we select one order across all observations, and we place them on a common reference frame. So in essence, we align them. Then we use a Gaussian process to model the concatenation of all of these orders through time. And in principle, this will also allow us to include time variability in our model if we do a proper selection of the Gaussian process kernel. On top of that, if we are truly working within a Bayesian framework, we could also easily introduce an accountability for the telluric modeling. If we model the tellurics at the same time we model the spectra and extract radial velocities, we could have a straightforward way of characterizing the uncertainties associated with this modeling process. So in short, our model will have 4 different types of free parameters. Those that will be associated with the telluric modeling, those that will be associated with the modeling of the stellar spectra, the kernel parameters, the amplitude and the length scale of our model, which will be constant for the concatenated orders, but can change from one order to the other. On top of that, we also have to describe the mean model of the Gaussian process, which will be the continuum of the spectra. And so we'll have mean parameters for each order of each observation. And finally, but not least, the relative radial velocity shifts that will tell us the difference in radial velocity between a given observation and another one. Those relative radial velocity shifts will also be shared across the different spectral orders of the given observation as we want to capture planetary signals. So after our MCMC sampler or something similar proposes one value for each of those parameters, we will generate the telluric model to correct the stellar spectra using, for example, TELFIT. And then we will align the stellar spectra using the relative radial velocity shifts. We will concatenate them all together. We will model them with the Gaussian process, and we will evaluate the log likelihood of our model. And we repeat this until our model achieves convergence, which might take a little bit. This will be the ideal model, but we also have a few problems, mainly related with the number of free parameters that we will have. If we simply consider about 25 observations and 20 spectral orders, we can quickly rise above 1,000 free parameters in our model. And for to give some context, Espresso has about 170 orders, so this will blow up very easily. If we remove the main source of free parameters in our model, the mean, the continuum of the spectra, for the same 20 spectral orders, we are now below 60 free parameters. Not good, but we can live with that. One option to do that is to normalize the stellar spectra using, for example, Racine, as shown in here. So I select the S1D spectra, I model the continuum with Racine, I normalize the spectra, and then I divide the normalized spectra into chunks of about 9,000 pixels to mimic the S2D spectra of Espresso. And then to this, let's say, sort of S2D spectra, I apply this GP model on top of that. To validate the model, what we do is implement a sort of a simplified methodology for now, just for see if the model will be feasible or not. So as I said, we ignored the mean parameters. And for now, we are also ignoring the pluricorrection step. So we go directly to the spectral modeling part. We apply this to simulated spectra, and we generate a simulated data set by selecting one observation and placing Gaussian distributions on each pixel that we have. We draw one random sample from each Gaussian distribution, and then we create a simulated spectra. We then inject a radial velocity shift, and we repeat this n times to generate a time series of stellar spectra. To this data set, we apply both SBART and this Gaussian process model. And in this plot, in the left side, you see on the upper part, the extracted radial velocity values, and in the bottom one, the residuals to the injected radial velocity signal. In this case, we are only using a single spectral order, and we see that both the GP model and the SBART can retrieve the residuals, can retrieve the injected signal with residuals with a scatter of about alpha meter per second, which is very bad. But if we now start using, let's say, 8 spectral orders, our residuals fall to about 20 centimeters per second, with the GP model and SBART being mostly the same, with the GP model being slightly better. So just to summarize and to not take much more time, we have a new Gaussian process model, and even with many simplifications on top of it, we are already getting results compatible with SBART. And so this means that it will be a very promising approach to extract radial velocities. Thank you. And if you have any questions.
So we've got time for 1 or 2 questions. And in the meantime, if we could get the next speaker to make their way up.
Hey, nice talk. A question. So because you use GPs, you will be able to kind of reproduce the stellar spectra itself, right? And is there any idea of looking at this low noise spectra that will be reproduced by your model?
Sorry.
Like, I mean, your model that you use, SBART, does it produce a spectra itself because you do model it, right?
Yes, in SBART, we are constructing a stellar template from the data, but then we could compare it with the predictions of this Gaussian process model after it is fitted.
Okay, yes. So you plan to do that?
Eventually, yes, not for now.
Okay.
Great, let's thank André again.